We are a team from Boston University's College of Engineering Biomedical Engineering Department. My name is Rachita, and this is Stephen and Thomas, and we completed our project as a part of Professor Darren Robilaire's lab, the BOT Lab. Today we will be presenting about our project called Hemoptics, and it is a ultra-fast near-infrared tissue oximetry device.
The need for our device stems from a limitation that clinicians face when caring for patients recovering from cardiac surgery. It is critical to the care of these patients that we measure their arterial and venous oxygen saturation. Currently, however, clinicians either use a pulse oximeter, which is physically simple and only provides arterial saturation, or a pulmonary artery catheter, which provides more of the information breadth that we need, however, is obviously extremely invasive as it must be inserted through the heart. This trade-off creates a space for what is called diffuse optical spectroscopy, or DOSE, in which pulsating or modulating light is sent through tissue. The outcoming light is then compared to known spectra of chromophore, and then we are able to extract the chromophore concentrations from this information, such as the concentrations of oxy and deoxyhemoglobin. The first step in our design process was to miniaturize certain key components of the benchtop system in order to include them in a portable, clinic-ready device to be used for clinical testing. We designed the enclosure for our device using a CAD software provided by Protocase, the company that we used to fabricate our final design.
To quantify the success of Hemoptics, we first looked at accuracy. To do this, we compared our device to the benchtop system using a set of 6 different tissue-mimicking optical phantoms, all with different optical properties. When analyzing accuracy, we looked at 2 things, the absorption coefficient μA and the scattering coefficient μS prime. Both of these coefficients represent the detected absorption and scattering properties of each phantom. When comparing this benchtop system to Hemoptic, you can see that all data points comparing the 2 systems fall along the 1-to-1 correlation line. To look at precision, we ran a drift test with all 5 functional lasers to compare our device to the benchtop system. Here it was found that the drift in amplitude was less than 1 decibel and the drift in phase was less than 5 degrees. Shown as an example, we have our 825 nanometer laser modulating at 100 MHz. In culmination of our research was an in vivo measurement taken with Hemoptics. The graph shows the absorption coefficient μA varying with the cardiac cycle. The major spikes in μA correspond with heartbeats because oxygenated blood is the main chromophore in the human body. We would like to thank the entire BOT Lab, especially Professor Robilaire, Matt Applegate, Ray Fistafon, and Fei Tang. Thank you.